Hello everyone, welcome back to the hypothesis test video lecture series. So today, after a bit of an introduction into what a hypothesis test is, we are actually going to be doing some hypothesis tests. Today we are going to be testing hypotheses about the population mean, granted that the population standard deviation sigma is known. So just some recap, remember that when your sample size is at least 30, the sampling distribution of sample means is normally distributed. So that means when the null hypothesis is assumed true, the p-value of a hypothesis test is the probability of obtaining a sample statistic with a value either as extreme or more extreme than the one in the sample data. And p is going to be the areas in either a left tail, a right tail, or both tails, depending on the type of test you have. So to use a p-value to make a decision, you're going to compare your p-value to your level of significance alpha. If p is less than or equal to alpha, then you are going to reject the null hypothesis H0. If p is greater than alpha, you are going to fail to reject the null hypothesis H0. Remember, failing to reject the null hypothesis does not mean that you are accepting the null hypothesis as true. It just means that you did not have enough evidence to prove it false. Also, the initial decision is always made about H0, but remember that each hypothesis test always contains two hypotheses, the null hypothesis and the alternate hypothesis HA. So after you determine the standardized test statistic, in this case it's going to be X bar, and you turn it into a Z-score in this case, or a T-score in the next section, you're going to do one of the following for your p-value. If you have a left tail test, P is the area in the left tail. If you have a right tail test, P is the area in the right tail. If you have a two-tail test, that means each individual tail is 1/2 of your p-value. So P is equal to 2 times the area in one of the tails. So what we're going to do is we are going to find a p-value for a left tail hypothesis test with a standardized test statistic of z equals -2.23. And we're going to decide whether to reject H0 when the level of significance is alpha equals 0.01. So they've already gone ahead and turned the test stat into a standardized test statistic z equals -2.23. And since we are going to be doing a z-test, you are going to look up -2.23 in the standard normal table. So the table value that goes with -2.23 is going to be 0.0129. Now, since this is a left tail hypothesis test, what that means is that the p-value is going to be the area in the left tail. The left tail is the area to the left of your z equals -2.23. Now, since the table value gives you the area to the left, and this is a left tail test, so it wanted the area to the left, that means this table value is your p-value. And that's just because this is a left tail test. So then we're going to compare our p-value, 0.0129, to our given alpha value, 0.01. 0.0129 is greater than 0.01, so that means that your p-value is greater than your alpha. When p is greater than alpha, that means you are going to fail to reject the null hypothesis H0. What that will mean in context and how we're going to interpret that is going to be dependent on the actual question and the claim in test. But this is the initial decision. You would then interpret this later back in the context of the problem. So what we're going to do for this next one is we're going to find the p-value for a two-tailed hypothesis test with a standardized test statistic of z equals 2.14. And then we're going to make a decision whether to reject H0 when the level of significance is alpha equals 0.05. All right, so since this is a two-tailed hypothesis test, that means you are going to have two z-scores, and they are going to be symmetric on either side of 0, and these two tails are going to be exactly the same. Each individual tail is 1/2 of your p-value. And over here, this z-score is equal to 2.14. Now, since this is a two-tailed test, it's going to have two symmetric standardized test stats. So over here, we're going to have -2.14. So then, since this is a z-test, we are going to look up negative 2.14 in the standard normal table. The negative one is easiest to look up because remember, the standard normal table always gives you the area to the left. So the standard normal table will give you the area of this tail to the left of negative 2.14. So look up negative 2.14 in the standard normal table, and you are going to get a table value of 0.0162. Now remember, that table value is just the area of one of the tails. Since the two tails are the same, this tail is also equal to 0.0162. So your p-value is going to be 2 times the area of one of the tails, which is the table value. So p equals 2 times your table value, 0.0162, gives you a p-value of 0.0324. Then we're going to compare our p-value, 0.0324, to our given level of significance alpha, 0.05. Well, 0.0324 is less than 0.05, so your p-value is less than your alpha. When p is less than alpha, according to that decision criteria a couple slides ago, we are going to reject the null hypothesis H0. And again, how to interpret that is going to depend on the problem. You would then interpret this initial decision in the context of the problem. So what we're going to do is we're going to be using a z-test to test claims about the hypopulation mean. So if you are trying to test a claim about the population mean, if you know the population standard deviation sigma, that means you are going to be using a z-test. If you do not know sigma, that is going to be what we cover in the next section, and that is going to be a different test. But these are testing claims about the population mean mu, assuming the population standard deviation sigma is known. So that means what we're going to do is our test stat is going to be our sample mean. So a random sample is going to be obtained, and the sample mean is going to be calculated. Then, when sigma is known, you are going to use a z-test for the mean. And there's actually going to be two different ways to perform a z-test. One of them is using p-values, which we're going to cover first, and the other one is going to be using rejection regions, which we're going to cover in a little bit. So to use a z-test, you first need to turn your test stat x bar into a z-score, and this z-score formula is going to be a little bit different than the one you're used to. This is actually the one from the central limit theorem. So the z-score is going to be your sample mean minus the hypothesized population mean, so the population mean in the hypotheses, divided by the standard error. So this is going to be the formula that you will use to turn your test stat x bar into a standardized test statistic z. And remember, this is for a z-test for the mean. This requires you to know sigma. If you do not know sigma, you can't use the formula that uses sigma. But the z-score is going to be the sample mean x bar minus the mean in the hypotheses mu, divided by sigma, population standard deviation, divided by the square root of n, the sample size. Provided you have a couple of conditions, provided that the sample is random, and either the population is normally distributed or the sample size is greater than or equal to 30. So here is the outline in words of how to use a p-value to do a z-test for the mean. And remember, to do a z-test for the mean, you need to know the population standard deviation sigma. So in any of these problems, please, every time that you are asked to test a hypothesis about a population mean, you need to make sure that you know sigma. If you do not know sigma, you cannot use the formula that uses sigma. So just make sure that sigma is actually known. That's the big one. Then you're going to state the claim mathematically. So turn the claim into symbols and figure out whether that is H0 or HA. Then you are going to write its opposite for the other hypothesis. By the end of step 2, you should have both H0 and HA. Don't forget, label which one is your claim. Then you are going to figure out the level of significance alpha. It'll be told to you in the problem. Then you're going to turn your test stat x bar into a standardized test statistic using this formula right here. Z equals sample mean minus the mean in the hypotheses divided by sigma over the square root of n. Then you're going to, based on whether it's you're going to find the area using the standard normal table that corresponds to your test stat z. Then you're going to use that table value to find your p-value. Remember, if you have a left tail test, p is the area in the left tail. If you have a right tail test, p is the area in the right tail. If you have a two-tail test, p is equal to 2 times the area in one of the tails. And remember, the type of test depends on the symbol in the alternate hypothesis HA. If HA contains a less than, it's a left tail test. If HA contains a greater than, it's a right tail test. If HA contains not equals, it's a two-tail test. Then you're going to compare P to alpha and then decide whether to reject H0 or fail to reject H0. And then you're going to interpret your decision in the context of the original problem. That will be where the labeling which hypothesis was your claim is going to make a huge difference. Remember, if H0 is false, that means HA is automatically true. All right, so for this first one, in auto racing, a pit stop is where racing vehicles stop for new tires, fuel, etc. The efficiency of a pit crew is essential. Pit crews need to work as fast as they can. A pit crew claims, so here we go, here's your claim, that its mean pit stop time is less than 13 seconds. Notice how they didn't say 13 seconds or less. They just said less than 13 seconds. So I'm going to translate that statement into math. That population mean is mu, is less than 13. Now, since this is just a less than 13, this is actually your alternate hypothesis HA. So HA is mu is less than 13, and I'm going to label that as my claim. Now, before we go on with the rest of the problem, we are going to get our other hypothesis, H0. So the opposite of less than is greater than or equal to 13. Then for the rest of the information that is given, a random sample of 32 pit stop times, so that means your sample size n is equal to 32. Has a sample mean of 12.9 seconds, so that is x bar. So x bar is equal to 12.9. Assume the population standard deviation is 0.19 seconds. So that is sigma, population standard deviation is 0.19. Is there enough evidence to support the claim at alpha equals 0.01? And because there is more than one way to do these, this is specifically asking us to use a p-value. So now that we've got all of our information, the first thing that we are going to do is we are going to turn our test stat x bar into a z-score using this z-score formula right here. So the z-score that goes with this test stat is going to be the sample mean, 12.9, minus the mean in the hypotheses, 13, divided by the population standard deviation, 0.19, divided by the square root of the sample size, 32. I'm sorry this is glitching out so bad. I don't know what the problem is. Remember, you can find the completed note outlines on Canvas. That'll allow you to see a little better. So when please put parentheses around the numerator and parentheses around the denominator when you plug this into a calculator. You should get rounded to 2 decimal places, get negative 2.98 for your z-score. So then we're going to figure out what our p-value is, and that will depend on the type of test. Since your HA contains a less than symbol, this is a left tail test, which means your p-value is going to be the area to the left of your test stat z. So the area in this left tail is going to be your p-value. So what we'll do is we will look up negative 2.98 in the standard normal table. And since the standard normal table always gives us the area to the left, that area to the left will be your p-value because this is a left tail test. So if you look up negative 2.98 in the standard normal table, you get 0.0014. Since P is the area in the left tail, and that is an area to the left, that means your p-value is 0.0014. So then we're going to compare our p-value, 0.0014, to our given alpha, 0.01. This is clearly less than, so p is clearly less than your alpha value. When p is less than alpha, that means you are going to reject the null hypothesis H0. Now, if you reject H0, that means H0 is false. So this claim right here was proven false. If H0 is false, the alternate hypothesis is automatically true. Since the alternate hypothesis is true, we're going to support the alternate hypothesis, HA. Since your claim was HA, that means there is enough evidence to support the pit-crews claim that the mean time is less than 13 seconds. So, because we are supporting HA and our claim was HA, we have enough evidence to support the pit-crews claim that their mean time is less than 13 minutes. Sorry, less than 13 seconds. You know what I meant. Now be very careful with the wording on this next one. Remember, if you want to try this one before I do it, just pause the video right now and then resume when you're done working. So, according to a study, the mean cost of bariatric surgery is $21,500. So, you think that this information is incorrect. You randomly select 25 bariatric surgery patients and find that the mean cost for their surgeries is $20,695. From past studies, the population standard deviation is known to be 2250, and the population is normally distributed. Is there enough evidence to support your claim at alpha equals 0.05? And we're going to use a p-value for this. Now, your claim was you think that this information here is incorrect. So the study says that the mean cost, mu, equals $21,500. You think that information is wrong, so your claim is that mu is different than $21,500. Now, your claim is actually the alternate hypothesis. So this is another instance where the claim was the alternate hypothesis. That means what the study said, mu is 21,500, is the null hypothesis. And then just to get this out of the way right now, since mu contains a not equal to symbol, this is a two-tailed test. And let's go through and identify our other values. So we have a random selection of 25 patients, so n is equal to 25. Those 25 patients have a mean cost of $20,695. So that is actually your sample mean, since this $20,695 was in the same sentence as the sample size. So X bar is $20,695. From past studies, the population standard deviation sigma is 2250. And we're going to test this at alpha equals 0.05. So the first thing that we are going to do is we are going to turn our test stat X bar into a z-score using the z-score formula given a few slides ago. So your z-score is going to be your sample mean, 20,695, minus the mean in the hypotheses, 21,500, divided by sigma, 2250, divided by the square root of n, so the square root of 25. Put parentheses around both the numerator and denominator, and rounded to 2 decimal places, you will get a z-score of negative 1.79. Then we're going to figure out our p-value from here. So the first thing that we're going to do is we're going to sketch this. This is a two-tailed test, which means we have two z-scores. Here's one of them. One of them was this negative 1.79. So this tail is going to be half of your p-value. The other half of your p-value is going to be this right tail to the right of positive 1.79. So let's look up 1.79 in the standard normal table. If you look up negative 1.79 in the standard normal table, you get a table value of 0.0367. However, that 0.0367 is just the area in this tail here on the left. P is the area of both of the tails put together, so your p-value is going to be 2 times that area in the left tail, which we found in the table. So P equals 2 times 0.0367 will give you a p-value of 0.0734. So then we're going to compare our p-value, 0.0734, to our alpha, 0.05. This p is clearly greater than alpha. So since p is greater than alpha, that means we are going to fail to reject H naught. If you fail to reject H naught, that means you do not have enough evidence to prove H naught false. If you do not have enough evidence to prove H naught false, you automatically fail to support HA. If you fail to support HA since your claim was HA, we do not have enough evidence to support the claim. So there is not enough evidence to support your claim that the mean cost is not $21,500. So if you have a fail to reject H naught, you do not have enough evidence to reject H naught, and you do not have enough evidence to support HA. And since your claim was HA, you do not have enough evidence to support your claim. Now, the other way that you can do a z-test for a mean is to use what is called rejection regions. Rejection regions are a very similar idea to p-values, but they are an alternative to using p-values. So what you're going to do is you're going to determine whether your standardized test statistic, z, falls in a range of values that would be a rejection region for the sampling distribution. So when your standardized test stat falls in the rejection region, it is considered unusual and you would reject it. So these rejection regions are separated from the rest of the normal distribution by what are called critical values. Critical values are z-scores that separate the rejection region from the non-rejection region. To find these critical values, you are going to use your inverse standard normal tables, since you will be finding a z-score that goes with a given area, and that given area will be alpha based on the type of test that you have. So a rejection region of the sampling distribution is the range of values, range of z-scores, for which the null hypothesis is not probable. If your standardized test statistic falls in the rejection region, then the null hypothesis is rejected. If it does not, then the null hypothesis is not rejected. A critical value, which we're going to call z0, separates the rejection region from the non-rejection region. So what we're going to do is to find the critical values to find those critical values z0, what you're going to do is you're going to first specify your level of significance alpha, and then figure out whether the test is left-tailed, right-tailed, or two-tailed. That will determine where your rejection regions are. Is it an area to the left? Is it an area to the right? Or is it an area in two different tails? Then you're going to find the critical values z0 using your inverse standard normal table. If it is a left tail test, you're going to find the z-score that corresponds to an area to the left of just alpha. If you have a right tail test, you're going to find the z-score that corresponds to an area of 1 minus alpha. So you're going to look up 1 minus alpha in the inverse standard normal table. If you have a two-tail test, the z-scores, one of them is going to be the z-score that goes with an area of 1/2 alpha, so you would look up 1/2 alpha in this inverse standard normal table. And then, its opposite will be the other tail. And then for rejection regions, you do need to make sure that you are sketching the standard normal distribution. You're going to draw a vertical line at each critical value and shade the appropriate rejection regions. And that vertical line, you're going to label it with your critical value. So we're going to find the critical value and rejection region for a left tail test with alpha equals 0.01. So the first thing I'm going to do is I'm going to draw my distribution. And our rejection region, since this is a left tail test, is going to be the area in the left tail. It is going to be the area to the left of our critical value, Z0. So since this is also a left tail test, that means your alpha is the area in the left tail. So the area of this tail is 0.01. So what we're going to do is we're going to look up 0.01 in the inverse standard normal table. Since the inverse standard normal table only ever deals with area to the left, and your rejection region would be the area to the left, that means the critical value that the inverse standard normal table gives you is your critical value. So if you look up negative 0.01 in the inverse standard normal table, you get Z equals negative 2.326. So that means that every z-score to the left of negative 2.326 is your rejection region. So everything that I have shaded here, you would reject H0. Everything that is not shaded would be fail to reject H0. So for this next one, we're going to find the critical value and rejection regions for a two-tail test with alpha equals 0.05. All right, so since this is a two-tailed test, that means your rejection region is going to be the area in each of these tails. So your rejection region, one of them would be over here, and one of them would be over here. Since this is a two-tailed test in a standard normal distribution, these two critical values are exact opposites. So one of your critical values, your positive one, is going to be Z0, and the negative critical value is going to be negative Z0. Now, alpha is the area of the two tails put together. So the two tails put together have a combined area of 0.05. That means the area of each individual tail is 0.025. All right, so what we're going to do is we're going to look up 0.025 in the inverse standard normal table. The critical value that the inverse standard normal table gives you is going to be this one here on the left. So if we look up 0.025 in the inverse standard normal table, we get a negative critical value of negative 1.96, and that is just this critical value here on the left. To find the critical value on the right, it's just its opposite, so positive 1.96. So that is how to find your rejection regions. So to actually perform a z-test for a mean using rejection regions, what we're going to do is we're going to shade our rejection regions. So, in this case over here, everything that I have shaded would be reject H0. That means this area in the middle would be a fail to reject H0. And then you're going to actually put your test stat Z on that same graph that you drew with your rejection regions. If Z is sitting in a rejection region, you are going to reject H0. If Z is not sitting in a rejection region, then you're going to fail to reject H0. Remember, for a left tail test, the rejection region is the area to the left of this Z0. If you have a right tail test, your rejection region is the area to the right of this Z0. If you have a two-tail test, that means the rejection regions are going to be both of these little areas, one to the left of negative Z0 and the other one to the right of positive Z0. So here is, in words, how to perform a z-test for a mean using rejection regions. Granted that the population standard deviation sigma is known. So you still have to check that. You still have to check that sigma is known. If sigma is not known, do not use the formula that uses sigma. Then, just like before, you're going to figure out what your claim is mathematically. So you're going to translate the claim into words, figure out whether that is H naught or HA, and then state the other hypotheses to get your two hypotheses, H naught and HA. Remember, the symbol in HA will determine the type of test that you have. Then you're going to figure out your level of significance alpha, and then use your inverse standard normal tables to figure out your critical values and determine and shade your rejection regions. Then what you're going to do is you are going to find the standardized test statistic that goes with your sample mean. So you're going to turn your sample mean into a z-score using this formula. Then you're going to actually draw and put your z-score on that same graph that you drew your rejection regions. If z is in the rejection region, you are going to reject H naught. If z is not in the rejection region, you are going to fail to reject H naught. And then remember, don't forget to interpret your decision in the context of the problem. That is why you need to label which hypothesis is your claim. So let's say that employees at a construction and mining company claim, so here we go, here is their claim, that the mean salary of their company's mechanical engineers is less than that of its competitors, which is $68,000. So I'm just going to translate that sentence into math really quick. They are claiming that the population mean salary is less than their competitors' $68,000. It didn't say 68,000 or less, it just said less than 68,000, so this is just a less than. That right there is an alternate hypothesis. So the alternate hypothesis is mu is less than 68,000. And I'm just going to make sure that I label this as my claim. The opposite of less than is greater than or equal to, so your null hypothesis is going to be mu is greater than or equal to 68,000. Also, based on the symbol in the alternate hypothesis, since the alternate hypothesis contains a less than symbol, this is a left tail test. So let's go through and identify our other values. So a random sample of 20 of the company's mechanical engineers, so your N is equal to 20, has a mean salary of $66,900. Since this mean was in the same sentence as your sample size, that is your sample mean X bar. So X bar is 66,900. Assume that the population standard deviation is 5,500, so that is sigma. And the population is normally distributed. At alpha equals 0.05, we are going to test the employee's claim. So the first thing that we're going to do is we are going to turn our X bar into a z-score using the same formula as before. So the z-score is going to be the sample mean, which is $66,900, minus the mean in the hypotheses, 68,000, divided by sigma, 5,500, divided by the square root of n, so the square root of 20. Parentheses around the numerator, parentheses around the denominator. You should get a z-score, rounded to 2 decimal places, of negative 0.89. So then what we're going to do is we are going to figure out our rejection regions. Since your alpha is 0.05, remember this is a left tail test, that means 0.05 is the area to the left of this critical value z naught. So if you look up 0.05 in the inverse standard normal table, you get a z naught of negative 1.645. So that means everything to the left of negative 1.645 would be a rejection region. So everything I have just shaded, you would reject H naught. And everything that is not shaded, you would fail to reject H naught. we're going to do is we're actually going to put our z-score, negative 0.89, on this graph here. And I'm going to change colors real quick. So remember, in the middle here is 0. Negative 0.89 is just to the left of 0, but not quite as far to the left as negative 1.645. So that right there is your z-score. Z is clearly not in the rejection region. Z did not get as far as negative 1.645. So Z is in the fail to reject H naught region. So that is going to be our initial decision. Since the claim was HA, there is not enough evidence to support the employee's claim that their mean salary is less than $68,000. Let's try that again. There is, I don't know what's going on with the subtitles. There is not enough evidence to support the employee's claim that the mean salary was less than $68,000. Remember, if you fail to reject H naught, you automatically fail to support HA. Since the claim was HA, there is not enough evidence to support the employee's claim. So the mean cost equals 13,960. That is going to be H naught because it involves an equal sign. It involves equality. H naught always involves equality. So in this case, your claim is H naught. That means that your alternate hypothesis, the opposite of equals, is not equal. So the alternate hypothesis, mu, is not equal to 13,960. Since the alternate hypothesis contains a not equal to symbol, this is a two-tailed test. And let's go through and find the other values. So in a random sample of husband-wife families, the cost of raising a child is $13,725. That right there is your X bar. Since it was in the same sentence as a random sample, that is your sample mean, so 13,725. The sample consists of 500 children, so that is the sample size, n equals 500. Assume the population standard deviation is 2,345, so that is sigma. At alpha equals 0.10, we're going to figure out if there is enough evidence to reject the claim. Since your claim is H naught, we're either going to reject the claim or fail to reject the claim. So let's turn our sample mean into a z-score. So z is going to be our sample mean, 13,725, minus the mean in the hypothesis, 13,960, divided by the population standard deviation, 2,345, divided by the square root of n, so square root of 500. Parentheses around numerator and denominator, giving you a z-score of negative 2.24. So then we're going to use rejection regions for this one. Since this is a two-tailed test, that means this alpha is the area in each of the two tails put together. So the area to the left of this negative z naught is going to be half of alpha. So this area right here is going to be 0.05. And the area over here in this right tail is also going to be 0.05. The easiest critical value to look up is the negative one. So in the inverse standard normal table, we're going to look up half of our p-value, 0.05. When you look up 0.05 in the inverse standard normal table, you get negative z naught equals negative 1.645. That means your positive z naught is positive 1.645. So everything that I have just shaded would be to reject H naught. So that is a reject right there, and that is also a reject right there. Everything in the middle is a fail to reject H naught. We're extra glitchy today. Alright, so what we're going to do is we are going to put our z-score negative 2.24 on the graph that we just drew. Let me switch colors here real quick. Alright, so negative 2.24 is clearly to the left of the center, and it is further to the left than negative 1.645. It's like right there. Z is sitting in the rejection region. So since this is in the rejection region, our initial decision is going to be to reject H naught. Since the claim was H naught, we have enough evidence to reject the claim. So there is enough evidence to reject the researcher's claim that the mean cost is $13,960. So that is it for z-tests for a mean. Remember, you do a z-test when the population standard deviation sigma is known. So I'm very sorry about the glitchy subtitles and the glitchy stylus. I don't know what is going on today, but hopefully if you look at the completed note outlines on Canvas, it'll be a little bit more legible and a little bit clearer, and hopefully the YouTube subtitles will be better. So thank you all very much for watching. In the next video, we're going to cover a hypothesis test for the mean if sigma is unknown. So stay tuned for that, and I will see you in the next video. Bye-bye.